So I want to talk about the chain rule. Chain rule, it has to do with differentiating nested functions. So if you have a function and another function nested inside the function f, let's say g is nested inside the function f. Chain rule says if you differentiate such a thing, f prime, you differentiate the outside function and then you leave the inside untouched, that just stays there. However, you multiply by the derivative of the inside function. That's what chain rule says. Okay? Now, this form doesn't look that convincing, so let me try to explain this using the Leibniz notation, and it looks more convincing if you read it in the Leibniz notation. Although, when you actually get to use the chain rule, this form is more readily useful. So, when I use the chain rule, I'm going to be using this, but when I try to convince you that the chain rule is true, I'm going to use Leibniz rule for it. Yes?
Putting g prime, the derivative of g of x, is it the same as putting it after the x? The prime,
I did not understand the question.
is this the same as this?
Okay. So your question is whether g of x prime means same thing as g prime of x. Yes, they're the same thing. All right. So let's think of it like this. Suppose you have y equals to f of g of x. Okay? And to differentiate this function, that means we're really asking, what is y prime? That's the question, isn't it? Now, this, in Leibniz notation, is really saying, what is dy dx? That's the question. So that's another way to say it. Okay, now let's rewrite what you see up here by using substitution. We're going to say u is equal to g of x. We're doing a substitution where u is equal to g of x. Then, what you see over here can be written in the following way. You see f prime, instead of g of x, because g of x is the same as u, I can rewrite it as u. Okay. And because g is same as u, I can think of this as a u prime. You're differentiating u. That's how it looks like. Okay. Now, this thing here means you're differentiating a function of f as a function of u. Okay? So when you actually get to write this, you can rewrite this as df, you're differentiating f with respect to u. Okay? And over here, this can be written as du dx. Okay? And since y is this function f, what you have is, you can rewrite this as dy du dx. Okay. So this is another form of the chain rule. So if you write it in Newtonian notation, this is what the chain rule looks like. If you write it in Leibniz notation, this is what the chain rule looks like. So let me just circle this to give as the argument to go from the Newtonian notation to Leibniz notation. And the Leibniz notation simply says dy dx is equal to dy du times du dx. That's the chain rule in Leibniz notation. chain rule in Newtonian notation, chain rule in Leibniz notation. Okay, so let me try to explain how you can make use of these chain rule. Maybe seeing an example might help you to understand what I mean by these things, okay? So first of all, let's say we want to differentiate sine of x to the fifth. So we see a nested function. X to the fifth power is nested inside the sine function. Okay? According to this formula here, the solution should be done as follows. First, you set u as the thing nested inside. So under this assumption, we're trying to differentiate sine of x to the fifth power, and because this is equal to u, sine of u d dx is what we are looking for. Okay, so dy dx, that's how you should think of it. We're trying to differentiate this function which we call y, and we're trying to differentiate dy dx. Okay. Now, what does the chain rule say? Instead of trying to differentiate this function by x, write it as d sine u over du times du over dx. Okay? Now, what's sine u differentiated by u? No, sine of u. Sine of x differentiated by x is cosine x. So if you differentiate sine u by u, what do you get? Cosine u. What's du dx? U is x to the fifth power, so if you differentiate x to the fifth by x, what do you get? 5x to the fourth, right? And then you can replace this u by x to the fifth power, and that's the answer. The answer is cosine x to the fifth power times 5x to the fourth. Now let me try to solve the exact same thing using this formulation, so that when you see the two methods together, you can kind of see why these two different notations really mean the same thing. Okay? So under this one, example 1, solution 2, we'll try to solve it again. Sine of x to the fifth power derivative means you have to first differentiate the outside function. What's the derivative of sine? Cosine, right? Leave the inside untouched, so it's x to the fifth, untouched. Then what do you multiply? The derivative of x to the fifth should be multiplied, right? 5 times x to the fourth. So this is what you get if you apply this. There wasn't even any steps necessary, right? And you get the exact same thing, okay? So that's what I mean by saying, oh, these two are both called the chain rule. It's just in different notations, okay? And as you can see, this one is easier to apply than using this one where you have to introduce u and take many steps, okay? So this is more useful in practice, in solving questions. But look at this. This is more convincing. Doesn't this look convincing? Why? Because if you multiply fractions, just forget for a moment that dy dx just means you're differentiating y by x. Just think of this as just two quantities divided, okay? Then you can see easily that du can cancel, and you get dy dx, right? So the simply just looking at these as multiplication of two fractions immediately allow you to view this as, oh, just cancel, and you get that. So in this viewpoint, the chain rule looks kind of obvious. It should hold, right? In this viewpoint, it's not that obvious. It's not that trivial. It's just a little hard to use. This is easier to use. Okay, now that kind of, that may give you another question as another, I mean, if you see this in that way, you might have wondered, why did Leibniz think about this symbol? Why did he use dy dx for the derivative? And there's actually a very natural reason for his writing of dy dx. See, if you recall, derivatives were the limit of the slope of the secant line. So when you take 2 points and you draw secant lines, you calculate the slope, right? It's change of y over change of x, right? And this change of x was what we call the h, right? And when we close this h down to 0, we then, when we close this gap delta x down to 0, we get some limit, and that limit is what we call the derivative. And Leibniz decided to call this that way. Right? So what he's really doing is, if you set delta x to be very, very small, close to 0, so this delta x becomes infinitesimally small, it's very, very small. Although they're both becoming 0, their ratios might give you something non-zero. It could be 0, but sometimes it could be non-zero. It could be some other number that's converging. And the ratios was what Leibniz called the derivative. dy dx by themselves, Leibniz called them fluxions. So like flux, something flowing. It's like, that's what he called. So dy dx, so when calculus was first developed, Leibniz called this calculus of fluxions. He was developing everything in terms of fluxions. Okay? But for us, dx, dy's are just very, very tiny objects, infinitesimal quantities, who by themselves don't have any value. They have value of 0, but their ratios could have some meaning. That's the way we're going to think. Okay? And therefore, although I made this cryptic proof that, oh, you can think of these as fractions and you can just divide them, you can, that kind of logic is not totally meaningless. It does have some meaning. These are ratios of infinitesimal quantities, so you can just cancel them and say this is true. Okay? So that's a very rough idea of the proof. I can show you the actual proof, but I'll decline. I don't think it's worth it. If you want to see the proof of the chain rule, there's a proof in the textbook. Please try to read that. We will just try to practice this with more questions and so that we can get used to it.